Hey TechKnowStuds, in this video we're going to get further into link state routing protocols and OSPF. So let's start going over OSPF and take a deeper dive into it. In this video we'll start out by talking about link state protocols and recalling some of the information we already learned with link state protocols. Then we're going to get into the databases with OSPF. We'll get into packets and the messages that are sent back and forth between the two routers. We're going to get into Dijkstra's algorithm, which is what OSPF uses to determine the shortest path. And then we'll get into the SPF tree and with the SPF tree, and we'll wrap it up by talking briefly around cost and what cost is. And remember, there are three components to what a dynamic routing protocol is. The databases, which we're going to talk about the OSPF databases, the messages that are being sent back and forth, and then finally the algorithm it uses to determine what is going to be the best path. The link state routing protocols is an interior gateway protocol, and some examples of this is OSPF version 2, version 3, ISIS, and ISIS for IP version 6. In a prior video, we talked about distance vector and how RIP sends the whole routing table back and forth, and that's how it transfers all of the routes, and all the route information gets from router to router. Well, as you know, link state works a little differently. Link state is a little more complex in how it operates. The communication, of course, goes between all of the routers, but what's sent back and forth is information on the links, the state of the link. So if a link goes down, that information is then sent to all of the other routers. So it operates quite a bit differently than sending the whole routing table. Since link state is more complex, it has a lot more features and a lot more control over your network. However, it does have some disadvantages. When it initially converges, then it can be a little bit slower because there's a lot more that's happening and a lot more communication that's happening. But once that communication is established, then any changes that happen after that, convergence happens really fast. Versus distance vector, it's still slow. So link state can have much faster updates once it's done its initial convergence. From a scalability standpoint, it can scale to much larger networks. From a resource usage, it has to constantly communicate and constantly keep up to date. So it will use up more resources. And when it comes to implementation, link state can be a little more complex because there's a lot more features that are involved. Anytime there's features involved and anytime there's more complexity like that, it can be more complicated to implement and set up initially. OSPF uses quite a few data sets for its algorithm, and it stores that data in databases. So one of the examples here is the adjacency database. A database is a table or multiple tables that make up the database. So the table at question here is the neighbor table. So the adjacency database has the neighbor table in it. The neighbor table is whatever is the neighbors to a router. So the router will have other layer 3 devices that it's communicating with directly. So if it's directly communicating to other devices through OSPF, then that will be found in the neighbor table. It's a list of the neighbors. It's unique to each of the router. Each of the routers has its own set of neighbors, and we can view that neighbor table by doing a show IP OSPF neighbor. Another database that is on OSPF routers is the link state database. The link state database essentially contains all the information needed to create the topology. So the table involved in the link state database is the topology table. It holds all of the links and the details about those links. So it's information about each of the links on the network. It contains all of the information of the links in the area. And so we'll talk specifically about area, but when we set up OSPF, we will define an area, and all of the routers, all of the links within that area is going to show up in our topology table. To see the topology table, we would type in show IP OSPF database. Then we have the forwarding database. This is the routing table. The routing table has a list of all of the routes, and it is unique to each of the routers, and we do a show IP route to see that. Oh, one other thing to specify is this topology table should be the same across all routers within the area. So here's an example of a topology and what those databases look like. Each one of these routers is going to have a neighbor table in it. And that neighbor table is going to be look different because R2 is connected to different routers than R1 is connected to. So they are going to have different neighbors, and those neighbor tables are going to look different. The link state database is going to have all of the links within the area. So in this particular one, it's going to have the links between each one of these routers, and it's going to be listed all on here. So the link state database is, once this network is converged, is all going to look the same on each one of these routers. And the router will actually be able to determine the whole topology from this link state database. Then we have the routing table. Now the routing table should have all of the networks in it, but it will have different next hops. So the routing table is also unique to each one of the devices, each one of the layer 3 devices on this OSPF area. So now how do all of the routers get the information needed to create all of these databases? Well, the answer to that is it's sending packets back and forth. It's quite active, in, at least initially, in how it's communicating back and forth. So the first type of packet that we have is the hello packet. The hello message that's sent back and forth is what establishes these neighbor tables. It says, yes, I am speaking OSPF, and I'm speaking OSPF for this area, and so let's communicate, and you are now my neighbor, so let's make sure. It also makes sure that that neighbor is up. So it sends these hello packets out often just to check to make sure that neighbor is still up. Then we have the database description. The database description is communication that happens to make sure that all the databases are synchronized, to make sure that there are no changes that need to be made and that everyone is speaking on this, that has the same revision number essentially of database. Then we have a link state request. So this is where if one router needs to get an update, it can send a link state request to get an update, and the link state update is a reply to that. And then we have the link state acknowledgement, an acknowledgement that yes, I have received your link state update. So each one of these routers is sending information back and forth, and it's sending these hello packets back and forth, making sure that the routers are still up. It's sending these link state updates back and forth to make sure that all of the devices have all the information it needs. Now, what that device has is information to create a whole topology of all of the networks in the area. So what does it do next? Well, it uses the Dijkstra's algorithm to figure out what is the fastest way to get to the end destination, to get to a certain network within these networks. And so Dijkstra's algorithm has been around for a long time, a lot longer than packet switching has been around. It's been around a lot longer than OSPF. So this is Dijkstra's algorithm is a way to find out the shortest path to a location. So you use the Dijkstra's algorithm to find the shortest path. Well, it's been applied to the OSPF. So OSPF uses Dijkstra algorithm to figure out what is the fastest way to a location. It takes all of this information and it creates a SPF tree, or shortest path first tree. And that tree is going to show all of the different ways to get to the end network. So for instance, let's say we're talking about this end network right here, this 10.2.0.0, and it's coming from this layer 3 switch that's over here. And how to get to that network, what it's going to do is map out every single path to get to that location, figure out then what the cost is to get to that location, and then based off of the cost, it's going to choose the lowest cost or the shortest path to get there. The Dijkstra algorithm creates a shortest path first tree, or an SPF tree. And what that looks like is this is our network over here. And R1 needs to decide how it's going to get to a network hanging off R6. Let's just say it's a 192.168.0.0 network. It needs to get to that network. It needs to figure out what is the shortest path. So it calculates all of the different ways it could get to that. So it goes R1, R2, R3, R4, R6, and then it can get to that network. Or it could go R2, R3, R5, R6. And you can see that it starts building this out, R2, R3, R4, R6, or R5, R6, and creating this tree. This is the tree over here that it's creating. It also sees it can go R3, R4, R6. So R3, R4, R6. Or go to R1, R3, R5, R6. So R1, R3, R5, R6 to get to the final destination, which is this 192.168.0.0. So this right here is the SPF tree that it creates. In this example right here, our network that we've been creating, it's very simplistic. Let's say we want to get from switch 1 all the way to this network 10.2.0.0. Well, there is only one path. And so we go from switch 1 to R1 to R2 to R3, and then to that network. So the tree is very simplistic. It's our sapling right here. It's just a single branch on here, and it hasn't really branched out because there's no redundancy within our network. Here's another example where, let's say this network right here is trying to get to this network over here. Well, this router can branch off into 2 routes here, and then it goes back down to a single router right here. So that tree is also fairly simple because the redundancy within this network is fairly simple as well. Once you have the full tree, it calculates it based off of bandwidth. And so it needs to choose what is the lowest cost to get to this network. Well, it does this by figuring out what is the cost of this. So maybe this is 1, 1, 1, and this is 19. So now it can take that and put it on this list here, and it sees that it takes 20 to go this route, and it only takes 2 to go this route. And so therefore, it's going to choose the lower cost of the two. In the rest of this module, we're going to take a deeper dive into the databases. We're going to take a deeper dive into the packets, and we're going to take a deeper dive into the cost. So we will be covering this a little more in depth as we go along. For now, what we have covered is the link state protocols. What are the differences? We talked about some of the databases with OSPF and how it uses packets to pass information back and forth. It uses the Dijkstra algorithm to figure out what the SPF tree looks like, the shortest path first tree, and then we wrapped it up by talking about cost and how it calculates cost and figures out what's the lowest cost to get to the destination network.